Already we have seen what is steady state error and error constants. Position error constant, velocity error constant, and acceleration error constants we have seen. Now let us see generalized error constants that we have to find. We know that E of S equal to R of S upon 1 plus G of S H of S. How we got? Here E of S, this is B of S. E of S equal to what? E of S equal to R of S, R minus C. That is equal to R minus C. Sorry. E of S equal to R minus B. R minus B. B equal to what? C multiplied by H. CH. C equal to what? EG. Therefore, HG. E you can substitute. Instead of C, we can put HGE. E equal to R minus, this is equal to H multiplied by C multiplied by G multiplied by E. You have to multiply all these, you will get B. Therefore, HGE. HGE. Or you can write E1 plus GH equal to R, or E equal to R upon 1 plus GH, we will get. That's what we wrote here. E equal to R upon 1 plus GH. Now, this can also be written as E of S equal to R multiplied by F of S. R of S multiplied by F of S. R of S multiplied by F of S, where F of S equal to 1 upon 1 plus GH. 1 upon 1 plus GH can be called as F of S. Therefore, E of S equal to R of S, F of S. Therefore, E of T equal to what? E of T equal to Laplace inverse we have to take. Laplace inverse. If you take Laplace inverse of E of S, you will get E of T directly. But this is product of two time frequency domain functions. If we take Laplace inverse, it will be convolution in time domain. It is convolution time domain. E of T equal to convolution of 0 to T F of tau R of T minus tau D tau. So convolution of two functions. Convolution of two functions. F of tau and R of T minus tau. The limit is 0 to T. What is E of infinity? Steady state error means E of infinity. That is limit T tends to infinity, E of T. E of T. T tends to infinity. Wherever you find T, we have to convert this into infinity. 0 to infinity, F of tau, R of T minus tau, D tau. So steady state error equal to 0 to infinity, F of tau, R of T minus tau, D tau. But we can write R of T minus tau in Taylor series expansion. R of T minus tau equal to R of T minus tau upon 1 factorial R dot of T plus tau square divided by 2 factorial R double dot of T minus tau cube upon 3 factorial R triple dot, third derivative, plus etc. plus tau to the power R minus 1 to the power R, because we do not know whether R is even or odd. For odd terms, negative. That's why we do not know r is even or odd. That's why minus 1 to the power r divided by r factorial. Sorry, k let us put same k factorial, kth derivative of t, kth derivative. That's all. Plus etc. Infinite series. This can be written as r of t plus sigma k equal to 1 to infinity minus 1 to the power k tau to the power k t kth derivative of r by dt. This can also be written as r of t plus sigma k equal to 1 to infinity minus 1 to the power k tau to the power k r kth derivative. This way also we can write kth derivative of r. Let it be 1. Let it be 2. If you substitute 2 in 1, what you will get? E of infinity equal to integral of 0 to infinity f of tau. Within bracket, you have to substitute this r of t plus sigma k equal to 1 to infinity minus 1 to the power k tau to the power k kth derivative of r d tau. So we replaced this r of t minus tau, by this expression. Now this can be written as E steady state equal to, this can be written as E steady state equal to, what is the first term? R of t f of tau d tau. So first term is integral of 0 to infinity r of t f of tau d tau plus, what is the second term? Minus integral of 0 to infinity tau r dash of t, first derivative f of tau d tau divided by 1 factorial. What is the third term? Plus integral of 0 to infinity tau square divided by 2 factorial r double dot, second derivative f of tau d tau plus etc. Plus, what is the rth term? Kth term, 0 to infinity tau to the power k divided by k factorial minus 1 to the power k f of tau d tau. So we can take this r of t is independent of integration because it is in t. Here integration is for tau. Here also r dash of t can be taken outside. These are all independent of integration. These are all independent of integration. independent of integration. That's why we can take them out. But this tau we cannot take out. Sorry, this tau you cannot take. This tau you cannot take. Here also tau you cannot take. This tau you cannot take outside. Therefore, we can write E steady state equal to integral of 0 to infinity r of t r of tau E steady state equal to r of t integral of 0 to infinity f of tau d tau, first term, plus what is the second term? Minus r dot of t, first derivative, divided by 1 factorial integral of 0 to infinity f of tau d tau multiplied by tau. This is second term. Third term is r double dot of t divided by 2 factorial integral of 0 to infinity tau square f of tau d tau, plus etc. plus kth derivative of divided by k factorial integral of 0 to infinity tau to the power k minus 1 to the power k. We do not know the sign. This can also be written as E steady state equal to this. This can be called as C naught, a constant, because integration with limit is a constant. Integration with limit is a constant. That's why we can replace this by C naught. C naught r of t. Integration with limit means a constant. Integration with limit is a constant. Therefore, C naught r of t plus this part, we can call this part as C1 plus r dot of t, C1 r dot of t divided by 1 factorial plus this minus sign is there, plus r C3 C2 r double dot of t upon 2 factorial plus C3 minus C3 r triple dot of third derivative of r divided by 3 factorial plus etc. plus CR CK kth derivative of r upon k factorial. That's all. Now we have to find C naught, C1, C2, C3, etc. CR we have to find. What is C naught? C naught is, what is C naught? C naught equal to what? Integral of f of tau d2 limit 0 to infinity. That is C naught. Integral of 0 to infinity f of tau d tau. That is C naught. I am deliberately multiplying to find something. I am taking deliberately, I am multiplying e power minus tau s. I am deliberately multiplying the integrand by e power minus ts deliberately, and I am writing limit s tends to 0 integral of 0 to infinity. S is independent of tau. S is independent of tau. S tends to 0. I am writing S tends to 0. it means if you substitute 0 here, what will happen? What will happen? That will vanish. It becomes 1. This becomes equal to 1. That's why I can include e power minus tau s. I am deliberately include. But integral of 0 to infinity f of tau e power minus tau s d tau equal to what? That is equal to f of s. Laplace transform. Definition for Laplace transform is f of tau e power minus tau s d tau. That is definition for Laplace transform. That is f of s. So limit s tends to is there. That's why this is equal to limit s tends to 0 f of s. So C naught is nothing but limit s tends to 0 f of s. Already we know f of s. If you come here in the first step, what is f of s? F of s is equal to 1 by 1 plus gh. 1 by 1 plus gh is f of s. There, if you substitute s equal to 0, you will get C naught. So if C naught we can find. C naught we can find. What is C1? C1 how to find? C1, what is the actual C1 expression? I am writing that expression. Integral of 0 to infinity tau minus tau minus tau minus tau f of tau e d tau. This is the expression. Minus is there. I am right deliberately. I am multiplying this by e power minus ts. Integral of 0 to infinity f of tau e power minus tau s d tau. I am deliberately multiplying this and I am putting limit s tends to 0. If I differentiate this with respect to s, what you will get? This is independent of s. This is also independent of s. Only term with respect to s is e power minus ts. If you differentiate this with respect to s, you will get minus tau e power minus ts. E power minus ts is same. If you differentiate e power something, any number of times it remains e power something. It remains e power something. So if you differentiate this integration with respect to s, the above statement you will get. Limit s tends to 0. That's why e power minus tau s will go off. And if you differentiate one time with respect to s, you will get minus tau. So the above the previous statement, this right hand side can be written as d by ds of limit s tends to 0 integral 0 to infinity f of tau e power minus tau s dt. We can write e power ts becomes 1 as s tends to 0. If you differentiate once, you will get minus tau automatically. That minus tau here, that minus tau automatically. So if you include these two terms, d by ds, limit s tends to 0, if you include these two, so we have to interchange. Limit s tends to 0, d by ds of, this is what, this is nothing but f of s. So take f of s, differentiate one time with respect to s, then let s tends to 0, you will get C1. What is C2? C2 equal to what? Here, this is C2. This is C2. That is what? Integral of C2 is integral of 0 to infinity minus plus tau square f of tau d tau. So what we have to differentiate twice. So limit s tends to 0 d square by dt square ds square integral of 0 to infinity f of tau e power minus tau s d tau. So if you differentiate e power ts twice, you will get plus t square. Every time you will get minus tau, it becomes plus tau. That's why tau square. So if you differentiate twice, you will get tau square. Therefore, C2 can be written as limit s tends to 0 d square upon ds square f of s. This is equal to f of s. This is equal to f of s. This is equal to f of s. This part is equal to f of s. That's all. F of s already we know. So if you want C2, differentiate twice. If you want C1, differentiate once f of s. Then let s tends to 0. Suppose you want C k, you have to limit s tends to 0, kth derivative of limit 0 to infinity f of tau e power minus ts d tau. So this minus 1 to the power k also you can take outside. Therefore, we will get limit s tends to 0, that is equal to limit s tends to 0, kth derivative with respect to s of, this is equal to f of s. This part is equal to f of s minus 1. What is steady state error? Steady state error equal to what? Steady state error equal to C naught R of t. Input we know plus C1 minus 1, because minus 1 you are getting from C1. That's why minus 1 is embedded in C1. Minus 1 is embedded in C1. That's why I have to put plus sign only for all. Minus 1 is embedded in C1. Therefore, C1 R dot of t divided by 1 factorial plus C2 R double dot of t divided by 2 factorial plus C3 R triple dot, 3 times we have to differentiate, divided by 3 factorial plus etc. plus ck, kth derivative of r divided by k factorial. That's all. We know how to find C naught, C1, C2, etc. ck. What is C naught? Limit s tends to 0, f of s. What is C1? Limit s tends to 0, derivative of f of s. What is C2? Limit s tends to 0, second derivative of f of s. What is ck? Limit s tends to 0, kth derivative of f of s. That's all. So we know the general expression for steady state error. Only thing is we want to know the input r of t. Suppose I know r of t. R of t equal to, suppose I know r of t equal to t. R of t equal to t. You can find the steady state error. I know the transfer function also. G of s also I know. G of s equal to 1 upon tau s plus 1. H of s equal to 1. H of s equal to 1. These are all given. Let us find. From this we can find C0, C1, C2, C3, etc. Because f of s equal to what? F of s equal to 1 upon 1 plus g of s, because h of s equal to 1. 1 upon 1 plus g of s is f of s. So we can find, as we know f of s, we can find C0, C1, C2, C3, etc. R of t, we have to substitute here. If you know C and C0, just to substitute R of t, you will get steady state error. So let us assume that C0 equal to 1. Therefore, steady state error equal to 1. C0 equal to 1. Let us assume. What is that? Not this transfer function. Some transfer function. C0 equal to 1 multiplied by t. That's all. R of t we know. But what is the first derivative of R of t? 1. Therefore, this R of t becomes 1. What is the second derivative of t? 0. What is third derivative of t? 0. That's all. Only 2 terms you will get. Only 2 terms you will get. We know how to find C0, C1. Just to substitute R of t and R dot of t, R double dot of t. That's all. Do you understand this? That's all. If you see some, you can understand.